Derivatives of logarithmic and inverse trigonometric functions. Let's start with the derivatives of logarithmic functions. So the derivative of log base b of x is 1 divided by x times the natural log of the base b. Let's see why this is true. If f of x is the log base b of x, we can rewrite this as y equals log base b of x. And because of the definition of a logarithm, this can be rewritten as b to the y power is equal to x. Now what I'm going to do is take the derivative of both sides with respect to x. So the derivative with respect to x of b to the y is equal to the derivative with respect to x of x. The derivative of b to the y is b to the y times the natural log of b times the derivative of the exponent, which is dy dx. And the derivative of x is 1. So to solve for dy dx, we will divide both sides by this, and that will give us dy dx equals 1 divided by b to the y times the natural log of b. But let's remember that b to the y is equal to x, so I can put x back in here, and that gives us dy dx is equal to 1 over x times the natural log of b. And this is the derivative of the function log base b of x. Now, this formula is important, but most of the time, the base of our logarithm is actually the number e. In other words, most of the time, b is equal to the number e. So if y is equal to the natural log of x, which means log base e of x, then the derivative dy dx will be equal to 1 over x times the natural log of the base. But the base is e, and we know the natural log of e is 1. And so this simplifies to 1 over x. And this gives us a simplified version of the original formula. The derivative of the natural log of x is simply 1 divided by x. And this formula is more important because the vast majority of the time, if we have a logarithmic function, it will be a natural logarithm. So as an example, let's differentiate the function y equals natural log of x cubed plus 1. So we just learned that when you have a natural logarithm, the derivative is 1 divided by whatever is in the logarithm. So in this case, it is 1 divided by x cubed plus 1. But now we have to remember that this is a composition of two functions. So we have to multiply by the derivative with respect to x of x cubed plus 1. And so this gives us 1 over x cubed plus 1 multiplied by 3x squared. And this is 3x squared over x cubed plus 1. For our second example, it's pretty much the same situation. We're taking the derivative with respect to x of the natural log of sine of x. So the derivative here with respect to x, and this is assuming that our function is y equals natural log of sine of x, is going to be 1 divided by sine of x multiplied by the derivative of sine of x. And this is 1 divided by sine of x multiplied by cosine of x, which can be written as cosine of x over sine of x. And let's remember that there is a trig identity that tells us that this is the cotangent of x. The previous two examples give us an alternative form of the derivative of a natural log. So if you have the derivative of the natural log of something u, the derivative is 1 divided by u, but then multiplied by du dx. Again, this is just the chain rule. Or to put it in different notation, if we have the natural log of some function g of x, the derivative is 1 divided by g of x multiplied by the derivative of g of x, which is g prime of x, and that can be rewritten as g prime of x over g of x. In this next example, f of x is the square root of the natural log of x. Now let's remember that we can rewrite this as the natural log of x quantity to the 1/2 power. So if I want the derivative of this function, I need to first apply the power rule of derivatives. And so f prime of x is going to be 1/2 multiplied by the natural log of x to the 1/2 minus 1. And then the chain rule says we have to take the derivative of the inside. And so this simplifies to 1/2 natural log of x to the negative 1/2 multiplied by the derivative of natural log of x, which is 1 over x. This can now be rewritten as 1/2 times 1 over the natural log of x to the positive 1/2. And then 1 times 1 times 1 is 1. And in the denominator, I have 2, I have x, and then the natural log of x to the 1/2 is the square root of the natural log of x. So the point here is don't forget your old rules about chain rule, power rule, etc. In the next example, we have f of x is equal to log base 10 of 2 plus the sine of x. So this gets back to our original derivative of log base b of x. So the derivative here is going to be 1 divided by 2 plus the sine of x, but also multiplied by 2 plus sine of x is the natural log of the base of the logarithm, which is 10. And then we also need to multiply it by the derivative of 2 plus sine of x. This is the chain rule. So the derivative of 2 plus the sine of x is cosine of x. So we get 1 over 2 plus sine of x times the natural log of 10 multiplied by cosine of x, which can be rewritten as cosine of x over 2 plus sine of x times the natural log of 10. So again, most of the time when you have a logarithm, the base here is not going to be 10. Usually it is going to be e, or a natural log. But every now and then you will see a log with a different base than e. In this next example, we're asked to take the derivative of the natural log of x plus 1 over the square root of x minus 2. So one way to do this would just be to use the formula directly. So the derivative of a natural log of anything is 1 divided by that thing. And then we would have to multiply by the derivative of this thing. Now you certainly can do this, but this will be rather complicated since to take this derivative you have to use the quotient rule, and then you also have to use the chain rule, and then you get a really complicated expression in the end. So although this can be done, there is a much easier way to do this. So if my function is y equals the natural log of x plus 1 over the square root of x minus 2, let's remember that we have properties of logarithms that allows us to rewrite this as the natural log of x plus 1 minus the natural log of the square root of x minus 2. And so the property we are using here is the natural log of a over b is equal to the natural log of a minus the natural log of b. Now furthermore, I can also rewrite this by viewing the square root of x minus 2 as x minus 2 to the 1/2 power. And then we have another property of logarithms that says if I have the natural log of a to the n, this is n times the natural log of a. So this 1/2 power can be brought down here. Now, just to be clear, I'm not taking a derivative yet. This is just a property of a logarithm. So when we rewrite this, we get 1/2 natural log of x minus 2. And again, this is the original function y, just rewritten. Now it is very easy to take the derivative. dy dx, the derivative of natural log of x plus 1 is 1 over x plus 1 times the derivative of x plus 1. Minus, then we have 1/2 times the derivative of natural log of x minus 2 is 1 over x minus 2 times the derivative of x minus 2. And this is equal to 1 over x plus 1 times 1 minus 1/2 times 1 over x minus 2 times the derivative of x minus 2, which is also 1. And so we can simplify this by writing it as 1 over x minus 1 minus 1 over 2 times x minus 2. And we can actually just leave our answer in this format, or you could combine your fractions together to get a simplified answer. Now, if you choose to combine these fractions together, you should end up getting x minus 5 over 2 times x plus 1 times x minus 2. And just really quick, if you don't remember how to do this, what you can do here is just get a common denominator. So I'm going to multiply this second fraction by x plus 1 over x plus 1. And I'm going to multiply the first fraction by 2 times x minus 2. And that gives us 2 times x minus 4 minus x plus 1 all over 2 times x minus 2 times x plus 1. And when you distribute the negative here, you should end up getting 2x minus x, which is x, minus 5 over the rest. So this answer here is a little bit better, but this answer here is acceptable. Before we do our next example, let's review derivatives of exponential expressions. There are basically 4 different types of exponential expressions. You can have a constant raised to a constant power, which of course would just be a constant. You could have a variable raised to a constant power. You could have a constant raised to a variable power, or in the most complicated case, you could have a variable raised to a variable power. So in the case of a constant to a constant, that's just equal to a constant. So if b and n are constants, the derivative of b to the n is simply 0. Now, what if you have a variable raised to a constant? So this would be something like a variable expression like f of x raised to a constant power n. Here you would use the power rule and get n times f of x to the n minus 1 multiplied by the derivative of f of x. So that's just the chain rule. In the next example, if you have a constant b raised to a variable g of x, this is just an exponential expression with base b. So the derivative of b to the g of x is b to the g of x multiplied by the natural log of b multiplied by the derivative of g. And we've gone over all of these pretty extensively, especially these two cases. We've talked quite a bit about these two. But in the last case, when you have a variable raised to a variable power, like f of x raised to the g of x, we need a new technique for doing this kind of a derivative. And the technique is called logarithmic differentiation. So let's do an example of this. Suppose I want to take the derivative of y equals x to the sine of x power. So notice that the base is a variable x, and the power is also a variable sine of x. So there are some steps that we can go through to take this derivative. The first thing I'm going to do is take the natural log of the left side and the natural log of the right side. And what this does is it allows us to bring this power down using a property of logarithms. So this becomes the natural log of y is equal to sine of x times the natural log of x. And now if you look at the right-hand side, we have a product of two functions of x. So we're going to use implicit differentiation, take the derivative of the left-hand side with respect to x, and the derivative of the right-hand side with respect to x. Now on the left-hand side, you have the derivative of natural log of y, which is 1 over y times the derivative of y, which is dy dx. And on the right-hand side, we have a product, so we're going to use the product rule. We're going to take the first function sine of x multiplied by the derivative of natural log of x, which is 1 over x, plus then the derivative of sine of x is cosine of x multiplied by the natural log of x. And so if we simplify this, on the right-hand side, we have sine of x over x plus cosine of x times the natural log of x. And on the right-hand side, we have 1 over y times dy dx. Now, we want to solve for dy dx, so the next step here is to multiply both sides by y. And when we do that, the y's here cancel out, and we get dy dx is equal to, and then the last step is I'm just going to replace this y with what it was in the beginning. And let's remember that in the beginning, y was equal to x to the sine of x power. So we have x to the sine of x times sine of x over x plus cosine of x times the natural log of x. And this is our derivative. So it's a kind of involved process, and it does take some practice to get better at it. But the main thing is you are taking the natural log of both sides in the beginning so that you can bring this power down. And then that changes it from a power to a product. And that allows you to use the product rule. So when you get more practice with this, it will get better. The next concept I want to talk about is the one listed here. The derivative of the natural log of the absolute value of x is 1 over x. This will come in handy when we talk about antiderivatives later on in this course. So let's talk about why this is true. So we know the definition of the absolute value of x is that it is equal to x if x is greater than or equal to 0, and it is negative x if x is less than 0. Therefore, the natural log of the absolute value of x would be equal to would be equal to the natural log of x if x is strictly greater than 0, and it will be natural log of negative x if x is strictly less than 0. So one quick comment to make here is the reason I can't include 0 down here is that we cannot take the natural log of 0. So now if I want the derivative of the natural log of the absolute value of x, I'm just going to take the derivative of each one of these. So in the first part, we're just going to say it's the derivative of the natural log of x, which is 1 over x, and this is if x is greater than 0. And in the second part, it's the derivative of the natural log of negative x, which is 1 over negative x times the derivative of negative x, which is negative 1. And notice that this is also 1 over x. So the derivative of the natural log of the absolute value of x is 1 over x, just like the derivative of the natural log of x is 1 over x. So again, this will be important later on when we talk about antiderivatives. Now we talk about derivatives of inverse trigonometric functions. So let's remember that when you say y equals the inverse sine of x, the meaning of this is that the sine of y is equal to x, and y has to be an angle between negative pi over 2 and positive pi over 2. So if I want the derivative of inverse sine, first of all, it's not the same as taking the derivative of sine. It's completely different. So we have no idea how to take the derivative if we have the inverse sine. However, if I take the meaning here of it, which is sine of y is equal to x, I can take the derivative of both sides of this equation with respect to x, and then using implicit differentiation, the derivative of sine of y is cosine of y and then times dy dx. And the derivative of x, of course, is just 1. And so dy dx is 1 divided by cosine of y. But what is cosine of y? So let's remember that when you have an expression, or an equation, rather, like sine of y is equal to x, you can draw a picture of a right triangle that mimics that situation. So in this right triangle, the angle here would be y, and if sine of y is equal to x over 1, we know that sine is opposite over hypotenuse. And so now I can solve for the missing side a here by using the Pythagorean theorem. And then solving for a, we would just subtract x squared from both sides, and a is going to be the square root of 1 minus x squared. So if a is equal to the square root of 1 minus x squared, notice that now you can tell me what cosine of y is. Because again, if I look at my triangle, here's the angle y, cosine is the adjacent side divided by the hypotenuse. So that is going to be the square root of 1 minus x squared over 1. And so cosine of y is the same as the square root of 1 minus x squared. Now, because of that fact, I can take the square root of 1 minus x squared and put it in place of cosine of y. And we get dy dx is equal to 1 divided by the square root of 1 minus x squared. And that is the derivative of the inverse sine. And this same process can be repeated for all 6 of the inverse trigonometric functions. Now, I won't do any more here, but they are all pretty much the same, and that leads us to the result. The derivatives of your inverse trigonometric functions are as follows. The derivative of inverse sine of x is 1 divided by the square root of 1 minus x squared. This is the one that we just proved. The derivative of inverse cosine, notice, is very similar to the derivative of inverse sine, except that it has a negative. The derivative of inverse tangent is 1 over 1 plus x squared. Derivative of inverse cotangent is a negative 1 over 1 plus x squared. And the derivative of inverse secant and inverse cosecant you can see here. And again, all of these can be proven using the same method that we used to prove this one. And I should say, just for clarity, that these 3 are the ones that you really need to remember. Those are the ones that we use the most. So let's take a look at the next example where we have g of x is the inverse secant of x squared. And we want to find g prime of x. So let's recall right here that if you have the derivative of inverse secant of x, it's 1 over x times the square root of x squared minus 1. Now what's different is we don't have x, we have x squared. So if x squared is taking the place of x here, then x squared needs to take the place of x here and also here. So the derivative g prime of x is going to be 1 over x squared times the square root of x squared squared minus 1, and then multiplied by the derivative of x squared because of the chain rule. So this becomes 1 over x squared times the square root of x to the 4th power minus 1 multiplied by the derivative of x squared is 2x. And then if we write this as a single fraction, we can express it like this. And then this x here cancels out one of the x's in the bottom, and we can simplify our answer to be 2 over x times the square root of x to the 4th minus 1. So derivatives of inverse trigonometric functions work like derivatives of everything else in that if you have a function inside of your inverse trig function besides just plain old x, you have to make sure that you multiply by the derivative of that inside function. So it's just the chain rule once again. And for our final example, we have a nice combination of several functions here. We have a natural log on the outside, and then an arctangent, and then t to the 4th. Now keep in mind that arctangent of some number x is the same as saying inverse tangent of x. So I can rewrite this function, if you want, as the natural log of the inverse tangent of t to the 4th. So what is the derivative g prime of t? Well, again, chain rule says you start on the outside function, and you're going to say the derivative of natural log of anything is 1 divided by that thing. And then we have to multiply by the derivative of that thing. And again, this is with respect to t. So now, what is the derivative of inverse tangent of t to the 4th? Well, on the previous page, we saw that the derivative with respect to x of inverse tangent of x was 1 over 1 plus x squared. But we don't have inverse tangent of x. We have inverse tangent of t to the 4th. So we need to put t to the 4th in here. So the derivative of inverse tangent of t to the 4th is 1 over 1 plus t to the 4th squared, and then we have to remember to multiply by the derivative of t to the 4th. That's the chain rule once again. And when you simplify all of this, you get 1 over inverse tangent of t to the 4th times 1 over 1 plus t to the 8th times 4t to the 3rd. And when you combine this all together, we can express it as 4t to the 3rd over 1 plus t to the 8th multiplied by the inverse tangent of t to the 4th. And this is about as good as we can write it. And so this is a great problem to end with because it kind of combines all the concepts that we've learned in this section. And that concludes this lesson.